Number 7 wasn't originally part of my video problem set for chapter 3, but it was requested in class, and after going over it in class, I realized what a good problem it is. So nitrogen, N2, and hydrogen, H2, react to form ammonia, NH3. Consider a mixture of nitrogen and hydrogen shown in the accompanying diagram. The blue spheres represent nitrogen. The white ones represent hydrogen. Draw a representation of the product mixture, assuming that the reaction goes to completion. How did you arrive at your representation? What was the limiting reactant in this case? Okay, so most of the time we're used to doing this on a mole level. But the way this one's framed, you're looking at it on a molecular level. So I have 1, 2, 3, 4 nitrogens and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. All right, when we balance the equation, when we react N2 with H2 to form ammonia, I end up with, for every 1 nitrogen, I need 3 hydrogens to make 2 ammonias. So I was given 4 nitrogens and 9 hydrogens. So the question is, which of these am I going to run out of first? The 4 nitrogens or the 9 hydrogens? So I ask myself a question. If I have 9 hydrogens, I mean, I could have asked it the other way, but I asked, if I have 9 hydrogens, how many nitrogens do I need to use it up? I use the coefficients in the balanced equation to convert from hydrogens to nitrogens. Well, so if I have 9 hydrogens, I need 3 nitrogens. Well, I have 4. So this tells me that nitrogen is in excess. I have 1 nitrogen extra that I need. All right, so that's what's going to be left over at the end of this thing. So a lot of people in class asked, where did the N2 go? Why isn't nitrogen always comes as a 2? That's true, and it's in its elemental form, but that's not what's happened here. Nitrogen has reacted. Nitrogen is no longer nitrogen anymore. It's ammonia. It's connected up with hydrogen to make something new. And the analogy I used in class was when you were a kid and you had a Lego airplane and you wanted to turn it into a Lego house. The first thing you had to do was tear it apart, pull all the Legos apart. Well, it's the same thing with these molecules. You have to pull the N2s apart and the H2s apart in order to put them back together to form something new. So the way they come back together is you have 3 hydrogens connecting to 1 nitrogen to make 1, 2, 3, 4, 5, 6 ammonias. And notice, right, the 1 nitrogen was left out. So this reaction stops when we run out of the white ones. The reaction's over. And nitrogen is in excess. My dog's whining in the background. It's time to go. Okay. Since I'm adding in this extra problem 7, I also wanted to make a correction to problem number 11. When we were balancing it in the first problem video, I balanced E wrong. The way you balance burning hydrocarbons is, burning a hydrocarbon, combusting a hydrocarbon, you're always making carbon dioxide and water. So the way you want to balance these is start with the carbons first. So I have 5 carbons going in, so I'd have 5 CO2s coming out. 10 hydrogens going in, it would mean 5 waters coming out. And then go back and balance the oxygens. Unfortunately, in my last video, I left out the fact that there are 2 oxygens in this hydrocarbon. So I left those out. So when I balance this thing, if I had 13 O's and I added those 2 O's, I'd had 15 going in and 15 coming out. Well, I can't get rid of that subscript 2 on that oxygen, so what I can do is talk about 13 halves. Multiply everything by 2 to get rid of that denominator. And now it's balanced. Okay, so now I have 26 plus 30 oxygens going in and 30 oxygens coming out.